Okay, so we talked about reaction energy diagrams and the Arrhenius equation there giving us some relationship between collisions and activation energy. And to kind of tie all that together, we want to kind of link what we know so far about kinetics to sort of an understanding of reaction mechanism. And the reaction mechanism, again, I think I've mentioned this before, it's kind of a step-by-step description of what happens in the reaction, what bonds are breaking, what bonds are forming, which molecules, which reactants need to collide with each other in order for this to happen. So what we want to be able to do is relate the rate law of the reaction essentially to the collisions that are happening, and vice versa, right? The collisions that are happening are going to show up in the rate law for the reaction. So experimentally, we can determine a rate law that should give us some ability to kind of understand what steps a reaction is happening in, what is the mechanism, and vice versa. If we have a proposed mechanism for a reaction, we can evaluate it with respect to the rate law, see if it matches the rate law, or if it maybe describes something different happening in the reaction. So one thing that we really need to think about that's going to be important for understanding a reaction, actually maybe two things. One is what's called the rate determining step. Rate determining step. And this very often is abbreviated as RDS. Right? This is the slowest step in the set of steps that make up the reaction. And when a step is slow, that means it has a high activation energy. So if we break a reaction down into steps, any step that occurs before the rate determining step or during the rate determining step, so the rate determining step itself, all of those steps, any reactant involved in that step will be part of the rate law for the reaction. Anything that happens after the rate determining step, since that's the slowest step, every other step by definition is faster, anything that happens after the rate determining step will not appear in the rate law for the reaction. It will be zero, something that shows up after that. Any other time it's involved in a collision will be zeroth order with respect to that particular reaction. Okay? And the other thing we want to think about, and this will come clear as I look at this reaction below, is during a mechanism we sometimes generate something called a reactive intermediate or just intermediate. This is a species that's formed in the process of a mechanism but isn't a reactant and isn't a product, right? And we kind of want to find those as we're looking at a mechanism because they do not show up in the rate law, right? But they might help us figure out which rate law is appropriate for a reaction. So looking at the example here, let's kind of investigate a couple of these possibilities. Now we're given the overall reaction here. We have bromine, 2 molecules of NO, right? And we're making this molecule where a bromine atom is now connected in to the nitrogen. And so that's the overall reaction. Here's one possible mechanism. We have 1 molecule of bromine combining with a molecule of NO, so some collision forming here, and we're making this molecule where we have 2 bromines attached to NO. Now, this compound, that's not a reactant, that's not a starting material, this is an intermediate. So the intermediate is formed during one step, and then it's used up in a future or subsequent step in that mechanism. So in the second step, that intermediate reacts with the other molecule of NO that makes the products of the reaction, that collision that is breaking one bond, forming another bond in the reaction. Okay, now, if this is the mechanism, there's a couple possibilities that we would want to be able to investigate. One is that the first step is slow relative to the second step. That would make the first step the rate determining step, or the RDS. Now, if that is the case, the rate law is going to look like this. The first step is slow. The collision that happens here between reactants, bromine and NO, those would both be part of the rate law. So Br2, I forgot K there, there'd certainly be a K. Br2 and NO, but they would both be first order in this particular reaction. Okay. We would not see an additional dependence on NO that happens in the second step, since that step is very fast relative to the first step. And the reason why is that this reaction would look like this. And you're going to keep the starting materials and the products fairly close together here. If the first step is slow, that means a large activation barrier. So there'd be a fairly high hill. Now there'd be a little dip here where that intermediate is, but then there'd be just a tiny hill for the second step of the reaction. So if we complete the first step of the reaction, we'd end up at the top of this hill. When you roll down, there's no way imagine a ball rolling along this line. It's not going to stop there. It's going to continue down. So that second step is going to happen very quickly. So we only see the first step in the rate law, and we get that for the rate law. Now, the other option, if this is reversed, the first step would be the fast step, and the second step would be the slow step. Now, if that's the case, right, everything that happens before and during the rate determining slow step is going to show up in the rate law. So we'd see this collision between bromine and NO to make the reactive intermediate, and then we'd see an additional dependence on NO colliding with the reactive intermediate. Now again, the reactive intermediate is not part of the rate law, so we wouldn't see that. So if that's the case, the rate law would be different, because now bromine would still be first order, but NO would be second order, because how fast the reaction happens is dependent on how much NO is around to collide in the first step and how much is around to collide in the second step. So this reaction energy diagram would look different. The first step would be a small hill, pretty easy to get over. The second step would be the large hill that's hard to get over. So pretty easy to get over the first step, right? Form the reactive intermediate. That reactive intermediate reacting with the additional NO would be going over this second hill. So we would see all of the pieces involved in both of those steps in the rate law.